Let's work on an example problem here, try and get a feel for work. And this will also teach us something about how we can get the most work out of something. A gas in a cylinder has a movable piston, so this is the thing that we've been talking about all through the day here. This gas occupies a liter, that's a volume, at 2 atmospheres, there's a pressure, and 25 degrees C. Pressure drops, so there's a decrease in pressure, and then the gas undergoes isobaric expansion, so the pressure stays constant and the volume increases until the gas is at 25 degrees C. The question is, how much work is done by the gas during this expansion? Well, let's sketch this situation out. Here's my container. Here's my movable piston. I know in here I have a volume of 1 liter. When the pressure that's on this is 2 atmospheres. Looking at my graph, here's volume, here's pressure. Pressure is 2 atmospheres, relatively high. Volume is 1 liter, right there. Then it says the pressure suddenly drops, so that's a switch to 1 atmosphere. And then the temperature is supposed to maintain Let's draw a physical model of this thing. Let's draw a physical model of this. Here's my piston. It encloses this volume of 1 liter when the pressure on the stuff is 2 atmospheres. Here's the graphical version of that. Here's volume, here's pressure. When my pressure is at 2 atmospheres, my volume is at 1 liter. Then it says the pressure suddenly drops. So now I have my pressure going from here down to here, 1 atmosphere. And then it says it expands isobarically. So then I go across like this, and I get to a new volume. I don't know what it is yet, but I do know that the pressure is at 1 atmosphere. But the temperature remains at 25 degrees C, so that means I'm on an isotherm here. If I'm on an isotherm, that means that Boyle's law holds. So I can look at this expansion and figure out what the volume is. The new volume, V2, whatever it is. I can figure that out because I now know the new pressure is 1 atmosphere. So Boyle's law says P1V1 is P2 times V2. So that means my second volume will be P1 times V1 divided by P2. And our first pressure was 2 atmospheres. And our first volume was 1 liter. And our second pressure was 1 atmosphere. So that means my second volume is equal to 2 times 1 divided by 1. It's just equal to 2 liters. Alright, I'm trying to find work here is what I'm trying to find. And work is equal to minus pressure times delta V. Well, the pressure that we're talking about is the pressure during the expansion, and that's 1 atmosphere. So I'll plug that in here, times the change in volume. Well, it started out at 1 liter, and it went up to, we found, went up to 2 liters. So the change in volume is 1 liter. Well, if I multiply these two together, I get 1 liter atmosphere of work. Doesn't seem like much of a unit of work, but it is. We're used to units of work that come in joules. We can convert. Here's one way we can convert. R, the universal gas constant, remember that was 0.0821 liter atmospheres per mole Kelvin. Well, R also is 8.314 joules per mole Kelvin, and that's useful in some other situations. Well, if these two are equal to each other and the moles times kelvins can just drop out, here's what that means. 0.0821 liter atmospheres really is energy. It's equal to 8.314 joules of energy. So that makes a conversion factor that we can use in changing liter atmospheres into the more familiar unit of joules. So let's do that with our quantity. We had 1 liter atmosphere, and we're going to multiply by this conversion factor of 0.0821 liter atmospheres equals 8.314 joules, and what we'll get is 101 joules. I've made a little error here. This is supposed to be negative, indicating that work is done by the system on the surroundings because it's an expansion. A quick rule of thumb is because 8 is about 100 times bigger than 0.08, you can take your liter atmospheres and just roughly multiply by 100, and that's going to give you pretty close to what the work output is in joules. Let's do this next problem. It's very similar to the last problem, except it happens in 2 steps, so it makes things a little bit more complicated. It's the same starting position. We have 1 liter at 2 atmospheres and 25 degrees C, but now the pressure doesn't drop to 1 atmosphere, it drops to 1.5 atmospheres, and then it does the isobaric expansion, and it goes back to 25 degrees C. Then after that happens, the pressure drops again, and now it goes all the way down to 1 atmosphere, and then it does its isobaric expansion and then gets back to the isotherm, 25 degrees. And the question is, what's the total work done by the gas during the 2 expansions? Now we have this expansion happening in 2 stages. Let's model the 2 stages with drawings. Here's our starting position, movable piston, in our container. We know our original volume is 1 liter. We know the pressure is 2 atmospheres. Then we change to this situation. We have an expansion that occurs under 1.5 atmospheres. And this is going to change to some volume we don't know, V2. And then we have further expansion because the pressure drops again. So now we're going to get another volume, V3, that we reach under 1 atmosphere of pressure. Let's call this first change step A, and then let's call the second expansion B. We want to find the total work, so the work is going to be the work in A plus the work for step B. Well, we're going to have to find V2 again. Thinking about what's going on here on this problem with our pressure volume curve, we are now starting at 2 and 1, 2 atmospheres, 1 liter, and we're now dropping to 1.5 suddenly, and then we're going back out to the isotherm via isobaric expansion. And so there will be some volume here, V2, we don't know what it is yet. Then we're dropping down suddenly to 1.0 atmospheres. So there'll be another drop, and then we'll go over here to some other volume, V3, isobarically. So that's what's going on in the graph. Well, let's figure out the work for the first step. Work for step A is going to be equal to minus the pressure during step A times the change in volume that happens during part A. Let's find out what V2 is. That'll be a good first step, and that way we can get delta V for step A. So using Boyle's law again, P1 V1 is P2 V2. V2 is going to be, like it was before, P1 V1 divided by P2. So that's 2 atmospheres times 1 liter of volume divided by our new pressure of 1.5 atmospheres. Atmospheres are going to drop out, volume is going to be in liters, and it's 1.33 liters. Okay, we wanted that so we could get delta V. So delta V is the ending 1.33 liters minus the starting 1 liter, so that means it changed by 0.33 liters. So the pressure during step A, that expansion, was 1.5, so the work in step A is negative pressure times change in volume, or negative 1.5 atmospheres times 0.33 liters. That works out to negative 0.50 liter atmospheres. And if we want to convert that into joules, remember the trick is 0.50 liter atmospheres is multiplied by this conversion factor. 8.314 joules is the same as 0.0821 liter atmospheres. And when you do this conversion, again, it's going to be about 100 times 0.5, which ends up being 50.6, negative 50.6 joules. So that's the work done in step A. Now, there's more work done, and that's the work that's done in part B. Let's go back and look at this a bit. During expansion V, we're going to get a new volume, V3, that we don't know yet, but the expansion is going to happen under 1 atmosphere. There's our isobaric change. That's the expansion. So we know P for part B is 1 atmosphere. Let's find out what delta V is by finding V3. So once again, Boyle's law holds, which says, in this case, P2V2 is P3V3. So that means volume at 3 is going to be P2V2 divided by pressure at 3. Our second pressure was 1.5 atmospheres, and the volume there was 1.33 liters. We found that just a little bit ago. Pressure 3 is 1.0 atmospheres, the final drop to temperature. Again, atmospheres are going to drop out, and I'll calculate V3. Well, V3 ends up being 2 liters, as you'd expect, because that was the final condition that was met in the first problem. So it's 2 liters. So what's delta V? Well, delta V for step V is going to be the ending volume of 2 liters minus the starting volume for that step of 1.33 liters. And that ends up being 0.67 liters. Well, now we can quantify the work for part B. Work is minus P delta V, so work for part B is the pressure under the second expansion times the volume change under the second expansion. Second expansion happened under 1 atmosphere, so that's P, and the change in volume we just calculated was 0.67 liters. So this comes out to 0.67 liter atmosphere. Well, let's change that work into joules just so we're consistent here, and that comes out to minus 67.8 joules. So now we can evaluate the total work that was done here in this process. Step A was minus 50.6 joules. Step B was minus 67.8 joules. So the total work done is the sum of those two, and it's minus 118.4 joules. Now, if you compare that to when we did this in one step, the last problem, the answer that we had there was only 101 joules. So when you do it in 2 steps, it looks like you get more work.